and welcome to the show on Blockleaders.io with me, Gillian Gossel. Today, I'm delighted to be joined by Dr. Davi Ortega. Am I saying your name right, Davi?
Yes.
Good. Okay, Davi, you are an accomplished scientist, Brazilian by birth and living in California. You're actually a postdoctoral scholar at the California Institute of Technology, or Caltech. So, Davi, thank you so much for coming on the show. I want you, first of all, to explain a bit about your day job. It's pretty, you actually were very self-deprecating. You said it takes patience to be a scientist. No, I think it takes brains to be a scientist. So tell me just
a lot more patience.
A bit about your day job.
Okay, so I am a computational biophysicist. Basically, I try to study evolutionary models that can explain the evolution of macromolecular machines. So you have bacteria, for example, these really tiny unicellular organisms that they have these little tiny machines inside that sometimes secrete stuff, or they rotate flagella so they can move. They can actually form a little processing machine for information. So they have receptors and distill a little bit of information. So I'm interested in understanding how these things actually appeared in the bacteria, how they actually evolved to become so complex. So for that, I use comparative genomics. I study a lot of comparative genomics, do genome context, bioinformatics in general. That's pretty much my day job now. And this is coupled with what my lab actually does, the lab that I work with. So I work at the Grand Junction Lab in Caltech. That is a cryo-electron microscopy lab. And
these words are so long. They have so. So tell me the name of the lab again.
Grand Junction. It's a Janssen lab. Is the name of my boss. And then he is actually a professor in biology. And then we use cryo-electron tomography to take pictures of bacteria.
Say that word very slowly for me again. Once more.
Cryo-electron tomography.
Okay.
So it won the Nobel Prize a few years ago, the technique, not my boss, but the technique, yeah. And then basically what we do, we we trap this bacteria into very thin ice.
That's the cryo mission.
Exactly, but we actually freeze them so quick that they don't explode. The water doesn't have time to explode this bacteria. So then we have like near native states of how things actually look like. And then once they're in this vitreous state, we can put in this electron microscopes that we basically take projection images, and then we actually tilt them a little bit and take several of these projection images. And with this tilting, we call tilt series, we can put them together and make like a 3D model of this bacteria. And then we can actually have a pretty good resolution about a 3D model for how these macromolecular machines work. So my lab takes pictures of them, and I try to actually relate the different pictures that we take from different organisms and how they actually, what are the evolutionary processes that actually had to happen for them to be different in the way that they appear in the pictures and so on.
So just tell me, so tomography, does that mean identifying the landscape of the electron?
No, so tomography comes from the fact that you take like different transmission images. So it's like a pass through, but because you're tilting it, then you actually have this idea of like a tomography, which is a 3D model of it. So you actually have to do some computations on top of that, and then you come up with like something that 3D that you can actually rotate and see in different directions.
I was thinking topography. That's where I got the landscape. Yeah,
wrong letter. Close enough.
So this is fascinating, right? And you were saying to me before, the microscopes, they're worth a lot of money.
Yeah, they are like around between like $3 and $7 million. And then there's all the accessories that comes with it, and the service contract for the people to take care of the microscope. So it's a lot of money. So
have you ever broken one, Davi?
Oh, it breaks all the time. It doesn't need to be it's not from we don't break them, but like it's a very delicate machine. Nowadays, it's much more commercialized. The new microscopes are really, really powerful. They're really robust, and they break much less. But 5-10 years ago, it was an endeavor. Like these folks are, and my boss been doing this job for over 15, almost 20 years. So back in the day when this entire field started to actually really become like a prominent, it was very hard to actually get this information. So imagine like a really expensive microscope, very highly qualified individuals. It's very few places in the world that can actually produce this data. Now it's a little bit more prolific. There's microscopes around the world, but still, it's not everybody that can afford one.
Wow. So as a result of this project, as I say, your boss has been on it for 15, 20 years. You've been working on it for 10 years. There's a lot of data.
No,
5 years, sorry, I beg your pardon. So there's a lot of data gathered.
Yeah.
And what was your concern about the data that was gathered, this expensive data?
Yeah, it's being, so you can imagine, right? Like you have these really expensive microscopes. And when we take this amount of information, which is a total 3D model of like half of a bacteria, we only use a tiny little bit of it for the research that we're looking. And the pretty groundbreaking discoveries you can make for tiny little bits of it. But it would be interesting to be able to reuse this data with everything else. So there was several discussions in our lab about how to, what can we do with all this data that was sitting in our basement. And my boss had this really good will to actually put this forward, to become like something public. And I'm Brazilian, so I understand how actually hard it is to actually have access to scientific data. So I volunteered to lead the effort to put this forward. And then the first thing that we tried to do was to reach out to centralized repositories. They reach out to us like, hey, we can actually do bulk, we can publish this in bulk and so on. But 30 terabytes of data, 11,000 different data sets in different file formats, it's not very easy to adjust everything to centralized repositories. So what we did was to try to develop a new infrastructure. We try to experiment with like new ideas about what can we do with these tomograms. And that's where the FLO blockchain comes into place.
And so, I mean, you're a scientist, and you said at the very beginning, you're not, you know, you're fairly new to blockchain. Would that be?
Yeah.
When did you first discover blockchain then?
I always mistaken this about like 4 or 3 years ago, something along those lines. Yeah. It's easy because it's on the chain, because the first time that I made the first application for the blockchain, I floaterized. It would be cool to actually talk about floaterize, but I actually floaterized the code as like my entrance into the field. So you just have to look back, and then there's that time, the first time I actually did anything useful with the blockchain.
So tell me a little bit about the floaterizer. If I'm getting the right, floaterizer.
The floaterizer was my first. I tried to actually start to study blockchain, and I got in contact with FLO from friends of friends telling me about this. And
may I interrupt you here? Sorry. Why did you choose FLO? Why that blockchain? What attracted you to, before you tell me about the actual DApp that you developed?
Well, I didn't know anything about it, but this is actually a funny story that I don't even know if the folks on the blockchain knows about it. But a colleague, a very good friend of mine, to be honest, from the Pirate Party in Brazil. The Pirate Party in Brazil, and then he is very knowledgeable about computers in general. He's pretty savvy, and he told me about this FLO blockchain. And at this point, I had this idea separate. How are we going to distribute it? 30 terabytes of data and 11,000 data sets of sky tomography. And then on the other side, like, I'm curious about what is blockchain. And it was a little bit before the hype of, I think it's the summer of 2017 when everything went crazy. It was a little bit before that when I started to get interested. So I actually landed on FLO by chance. And then the beautiful thing about FLO is like, oh, you can put data into the blockchain. I was like, excuse me, what do you mean put data on the blockchain? What does that even mean? But then I realized like, oh, this is a pretty cool idea, right? It's persistent storage. You put something there and it's gonna be there forever.
That's a beautiful name, by the way, term, persistent storage.
Yeah,
thank you.
It's a persistent storage for the history, right? Like you can put anything you want. it can be very dangerous. I'm very concerned about like the bad implications about this, but there are also good parts of it. So it's hard to invest in the good side of persistent storage. So one of the things that I learned was I thought about it was like, okay, so this is basically a notary. So you actually can put something there and it will stay forever. But I have a lot of being from the private party and collaborating with them a lot. So I'm concerned about privacy a lot. And I was like, how can I actually use the blockchain to make sure that people know that I have something as like a proof that it exists, and without telling anybody what I have. And that's what pretty much what like cryptographic hashes are. So you can actually just take a content and then you run a cryptographic hash, you get like a number, but it is encoded like letters and numbers. And then you can, this number is quasi unique to that content. There are some collisions, but it's almost unique. So then I can actually have a contract. I was kind of moving, so I can have a contract of renting an apartment with pictures attached to it. And I can send to the blockchain just the hash of it. And nobody knows what I have. But the hash gets timestamped. So if later on I get challenge of the existence of the photos or of the contract up to a certain date, I can just show the contract, and then they can actually run, they can calculate the hash by themselves, and I can show them a hash that's been timestamped before. And there's no way you can have the hash without having this document. So it's pretty much like a notarization. And then I built the floaterizer.net, which is a free service that anybody can use. You just go there and click upload. I think it says upload right now. A couple of friends actually helped build the latest graphic interface, but you just click upload, and then it doesn't upload anything. It takes the file inside your browser or inside your phone, and it doesn't send anywhere. Calculate the hash, and then send the hash to the server that actually runs the transaction and then broadcast the transaction for you. Actually, we can automate this now to actually everything be on the client side. But in any case, I didn't want to actually have people to have to pay for it, because when you put things in Flow, on the Flow blockchain, you have to pay a fee for the miners, right? Like part of the protocol. I didn't want people to actually need to have Flow to have a service like this. So I have a server that it runs on my dime, which is pretty cheap. But it runs on my dime, and then I'm happy to actually keep this running forever. So if you have a contract and you want to make sure people can challenge, you can just go to Floaterizer and it's free. And then you get like a little document showing this is your tax ID, this is where how you can find your transaction again. And
you were saying it's proof of existence.
Yes, that's the term that I think the field agrees. And this is one of the problems that I have. I mean, I don't have time to study everything that has been done. So we end up reinventing the wheel all the time. And sometimes there are people better than I doing this work, and they have better names than I do. So it's always like nice to actually expose a little bit the work that we do, so then we can get feedback. And then people are like, hey, by the way, we already done this, and this is the right name. And it's like, oh, sure, thank you. Okay, great. And it's good. Like this is like how we learn and how we actually exchange ideas with the community. So I guess that's the proper term, proof of existence.
No, it's cool. It's cool. It's a cool name, and it's very memorable. So then the next thing then was, of course, was the Openness Protocol. What is this, and how did that develop naturally from the work you were doing here?
Yeah, so I stumbled upon the Openness Protocol when I was trying to actually post things on the FLO blockchain, because I started to use the open source programs that have been developed around FLO to put data into FLO. And that most of this work was done by a startup company in San Diego called Alexandria. They changed a little bit the name, but they're now the Alexandria Lab. And
based on the ancient library, isn't that where the name came from?
That's right. That's right. Yeah. I think,
Of Alexandria.
Library of Alexandria.
Yeah.
That's right. So their goal was to actually try to come up with, make FLO to become the index of information in the world. And they developed a protocol to actually execute this, to how to actually formalize how you actually read and write information from the blockchain. it was early days at that time. Things were a little brittle. But then I contact them like, hey, I have this 11,000 tomograms and let's work together. And then they're like, hell yeah, let's do it. So it was nice because our contract took longer to be finalized between us, a nonprofit at Caltech, and a startup company, Alexandria. It took longer to finalize the contract than the project. The Openness Protocol, it was so easy to actually enter. Like it had such a low barrier for us to start developing using it, that within a week and a half, we had a reference implementation running, and our data was already in the blockchain. And then a few more weeks for us to actually develop a gateway, so you can actually communicate. We call gateway the graphic interface that you actually see on when you go to the website. So the website is etdb.caltech.edu. And then what you see there is the metadata comes from the blockchain, and the data comes from this interplanetary file system, or IPFS, which is also a distributed file system on the internet. So we came up with the publishing model that Alexander was already experimenting this, and we applied that to they're using this for media, and then we apply for science. So the way it works is once you have a piece of data, for example, a file of a tomogram, a tomography data set, you take this data, and then this data is, well, first, this data is useless if you don't know what it is, right? You have to know what you're looking at, how it was made, like what are the equipment that was used to produce this, and et cetera. So this is what we call metadata, is the information about the data. And then, so we need to actually find a way to actually push this data out and to have the metadata with it. Otherwise, you cannot reuse this. It's just useless. At least it's pretty, but not for scientific work. So the way our publishing model now is this. So we take the data, we put it on the IPFS. The IPFS gives us an identifier. It's a unique identifier for the data. We take this identifier, we mix with the metadata about the data, with all the information about like what type of bacteria you're imaging, like how many field series was taken, like all the voltage of the microscope, like all this stuff goes in there. And then we take that, we put this together, and we encode this using the Openness Protocol, and then we send this to the FLO Blockchain. Now, if somebody wants to actually find a cryo-electron tomogram, they can search the blockchain. Like, I want a tomogram. Well, of course, there's better ways to actually do the search, but like, I want a tomogram of Escherichia coli. And then it will return a result of like all these like records related to tomography data sets from E. coli, from Escherichia coli. However, it also comes the metadata about all the information that you need and the hash on the interplanetary file system. So now you go to the interplanetary file system and collect the data, and now you have both pieces. So the most important part about this is actually two important points. One, the user that actually is consuming this data don't need to talk to us, right? They talk to the interplanetary file system and they talk to the FLO blockchain. They never actually really need to talk with our servers ourselves. And the other thing is, if somebody else from another lab wants to contribute to this database, they don't need to ask us as well. They can just go to the blockchain and put their tomograms in there, done deal, and we'll be part of this.
How do you maintain quality if anyone can load up their own tomograph?
We don't. That's the interesting thing. So it is a public database. It's nobody's responsibility to keep things in high quality, but the person who is actually putting the data there. And when you build gateways to actually visualize and make this information more digestible for the user, we can select what type of data we are showing from who. So for example, another renowned lab decided to put 10,000 tomograms, but like some person with a lot of time in their hands decide just to put like improper content and call as a tomogram. We can select to never show this kind of like data, only show our tomograms and the tomograms from this other lab, because every record that goes on OIP is signed with the FLO private key. So we know we have like ownership of the records straight out of the gate, and it's basically for free, basically coming from the blockchain. So it was like just really good stuff, or good positive points, and we don't have the responsibility to maintain quality. We have the responsibility to maintain quality of our tool, of our content. And the other thing that is obvious about this is another lab joining in. They have a trade-off between adapting the data set to be compatible to us. So then when you search both. You search all our 11,000 tomograms and their 11,000 or whatever the number that they put, and the amount of work that it needs to actually put this information there. So there's a balance, and they can adapt the way they want. And maybe they want to just accommodate some of the fields that we developed, and then they want to put different fields on it. It's all up to them, and it's all up to whoever actually is putting the data on.
So this distributed database of anything, as we were saying earlier, so it's open to the public, it's freely available. What type of people will actually be accessing these tomographs?
Well, so this is a very interesting point. So the cryo-electron tomography was a one-time job. So we actually developed that, and then we put this information on it, and it was a great experiment. Like, people can access. This data is being used in several different other publications. So we're kind of really happy with the outcome. Now, we saw the power of it, right? Because other people not doing electron tomography, it's doing, I don't know, collecting rocks, or geologists, not collecting, but like studying rocks. And then people doing light microscopy, where you actually have simple pictures, or even like transmission electron microscopy, where you just take what we call electron micrograms. There's like this use case. So the next thing that our lab was challenged to do was to take 500,000 electron micrographs that we took from different environmental samples, and how we're going to distribute them. So if you use the same system as the cryo-electron tomography database, the ETDB, it will become very cumbersome, because then ETDB repeats the same metadata over and over again, because the number of data sets, 11,000, aren't that big. So we actually say it was taken with this microscope, with this voltage, with this, and that, like thousands of times. That's actually counterproductive, but it was our first pilot. So how can we generalize this, and how we can make this data more usable? So we team up again with Alexandra on our second project, which is trying to develop a system that will be even more permissive, more flexible. And we develop a system that is the version 0.5 of the Openness Protocol, where now the users, anybody, can put a new schema for the metadata, a new table on the database of all the content that OIP has. So it turns the OIP actually into a database of anything, because now you can actually start a new table, put a new type of data into the database, just simply by publishing what we call template of like how the data should look like. Basically the fields that you need to fill it up. So I give this example. If you want to make a database template of people, then if you want to make a database of people, you can just go there and select, I'm going to make a template. I want to put the name, the surname, the date of birth, place of birth, and this and that, and like description, and you press go. And as soon as you do this, the Openness Protocol understands what it's trying to do, send this data for the blockchain. And now we developed what we call DDX nodes. Used to call OIP nodes, now we move into DDX nodes, so like distributed database of anything nodes, who collect the information. This nodes collect this information, then assemble this into databases locally. So again, you still don't need to actually permission for reading this data, but you're actually reading directly from the data from the blockchain and actually putting this together into this database of anything, as we mentioned. Wow.
So are you more of a scientist now or a programmer?
Hard question. I'm not a programmer. I have terrible habits. I study, I try my best to do best practices, but I'm.
You're a scientist.
Yeah, I am.
I suppose you're. And you're a data scientist. So I mean, it's all that, and you have patience. Because
a lot of patience, yeah.
Yeah, I just the small one I'm listening to it, because it is very complex. and there's all those very big long words. And but I say, even the fact when you're taking the tomographs, it's like it's a lot of work. It's fascinating.
Oh, nowadays they do that very quickly, but beforehand it was kind of slow.
Okay, so
but yeah, like the patience was mostly to actually learn what everybody else has done, so we don't reinvent the wheel all the time.
That makes
sense. We have to study a lot about like what people have done, so we give credit for the work that came before us, and we can, as people say, step on the shoulders of giants and do our work from there on. So OIP is a case like that. So instead of reinventing the Openness Protocol, it was very nice to team up with who actually created and made like a whole lot better.
Fascinating. I have to say thank you so much for your time. Absolutely fascinating. I've learned a lot today. I certainly have. Whether it stays in my head afterwards, I don't know. There's a lot of learning there. But thank you so much indeed. I'll hopefully talk to you again for the next installment.
Absolutely. Thank
you so much. That's Dr. Davi Ortega, who is a postdoctoral scholar in the California Institute of Technology. Thank you very much for your time today.
Thank you.